Hello, everybody. This is the lesson for Friday. And I know that not both sections meet today on Friday. And so if the other section that's not meeting today gets wind of this, they can look at this screencast if they want to. I will just be going over this lesson on Monday. So as you can imagine, the story leads us to differential equations that are not exact. And what do you do with those? And I think my title here kind of gives it away. Sometimes there is a possibility of turning a non-exact diffie-q into an exact diffie-q by finding a particular integrating factor. And I should just say, too, this word, that vocabulary word, integrating factor, means a factor that you multiply a differential equation by that then makes it integrable or antidifferentiable, okay? So as the name suggests, that's what that means. So remember, the criterion for an exact diffie-q is this right here. And I use some subscripts, or I ignored some notation like, that m here is a function of x and y, n here could be a function of x and y. And the criterion is that m sub y equals n sub x. The partial derivative of m with respect to y equals the partial derivative of n with respect to x. If m sub y doesn't equal n sub x, is there something that you can multiply the diffie-q by? Okay, there's that word integrating factor. Is there something that you can multiply the differential equation by that would create essentially new functions of m and n? Right? Because if you multiply a differential equation, if you multiply this diffie-q by an integrating factor, and if that integrating factor is a function of x and y, then essentially you will have new m's and n's, right? But with those, is it possible to create an integrating factor such that the new function m and the new function n do satisfy the criteria for exactness? And the answer is yes, sometimes. Okay, and we'll go over and we'll, of course, talk about the cases where the non-exact diffie-q can't be made exact. What do you do then? But for now, we're going to look at the sometimes cases where a non-exact can be made exact. Now, I will say, this method is a really nice and lovely proof. I really like it. It's a proof that I usually do interactively with my class. It's very followable. It's very simple, but it's quite ingenious too. And so, I would be kind of having a back and forth with you here, but unfortunately, that can't be the case. So we'll do our best. All right, here we go. So let's go through the proof here. And it's really lovely. Proof sometimes can be so incredibly elegant and just lovely. Given a diffie-q where m sub y doesn't, whoops, there's my first error. Look at that, where m sub y doesn't equal n sub x. Let mu of xy be a function such that, okay, so what we're saying here is, I'm just calling mu sub xy. And the reason why I used mu, until I taught diffie-qs here last year, I always just called this function g or something, but your text uses mu. I don't know why. And so I just use mu because in the instructions they may refer to mu. But anyway, let there be some function of y, okay, that is essentially the integrating factor after all, right? Such that when I multiply the diffie-q by mu, which is the function of x and y, I have now a new m. And just to be clear, the new m now is this, right? This is the new m. It's mu of x of y times the function m of x comma y. The new n is mu of xy times the function n of xy. Yes, I didn't put the function notation next to the capital M and capital N. I'm just being a little bit shorthanded with that. That's kind of known information. All right, so essentially what I'm saying is call the integrating factor that would then make the diffie-q exact mu of xy. Okay, so this is the potential integrating factor that hopefully we'll be able to find. And if we're able to find the integrating factor, then we can create a diffie-q that is exact and then proceed as we do. So we have this new m and new n now, and then again, don't forget, the criterion for exactness is d by dy of the new m, right? So don't forget, this is now the new m, d by dx of the new n. These are now exact, okay? So what this means, though, the left-hand side, where we're taking a little bit a stroll through multivariable here for a second, What that means, if d by dy of a product of functions equals d by dx of a product of functions, I have to use the product rule on both sides. So here's the product rule on both sides of the equation, right? The product rule, the differentiation of this product with respect to y, the differentiation of this product with respect to x. Really nice and straightforward, right? Here's where it gets so incredibly clever. I think you'd agree that we're allowing for the integrating factor mu to be a function of x and y, right? I mean, after all, my differential equation is a differential of potentially some function of x and y.
What's your first
Okay, but what we're going to do is make our life much more infinitely simple. Wouldn't it be nice if that integrating factor mu was just a function of x or just a function of y? It would be nice, right? We have to allow for both possibilities. We have to basically work out what we would do, what mu would be in both cases. But let's just take case number one. Let mu of xy just be a function of x. So mu of xy is not an expression that involves x and y. It's an expression that just involves y. Well, if we make the case that let mu of xy just be a function of x, it obviously follows then that mu sub y has to equal 0, right? Okay, so then this equation up here, this blue equation, right, simplifies, because if mu sub y equals 0, you know what zeroes out? What turns into 0? If mu sub y equals 0, then look, this term zeroes out, right? I'm going to erase that because I want to go back to that in a minute. Well, and if u sub... No, that's not right. No, yes, it is right. Sorry. Yes, u sub y becomes 0, so this u sub y is dropped out, and then this blue equation simplifies to just right here. Really nice. It's such a lovely, lovely proof. Proofs that are just really simple, yet also ingenious. That's actually arguably the definition of mathematical elegance, is that a really profound idea is arrived upon in a very, very simple, concise way. Okay, then all I did here, what I do in the next step, I just collected my mu terms, right? Mu terms, and then I factored mu out. And then what I do here, then I just took mu sub xn right here. I subtracted this term over. I set it equal to 0. And then it looks like I divided everything by n, right? I divided everything by n. And, oh yes, this was nice. In order to make this minus sign a plus sign, all I did was just distribute the negative into the parenthetical, and I have this in the numerator. Okay, I'm going to let you sit right here, and I want to ask you, anyone see something? Anyone? Anyone? I think right now this is my big section, right? And Leo, maybe you decided to come to the big section. Usually in these moments, when Leo discovers or sees something, he kind of elevates out of his chair, abruptly, I should add. What does this look like, everyone? Anyone? Pause me, because if you see it, it's pretty awesome. Pause me if you see it. Anyone? What if I wrote it like this? What if I wrote something like this? Because u sub x, if u is just a function of x, right? U sub x looks like that, plus, I'm just gonna do this for right now. I'm gonna box this whole thing and just go like this, plus box. U equals 0. Anyone? Anyone see something? What have we got here? What do we have? What is this? Yes, this is what is it, everyone? It is a linear standard form. Diffie-Q. Linear standard form Diffie-Q. Yes, it is. Yes, it is. Exactly. And um, and in these situations, when you had a linear standard form diffie-q, u of x is the integrating factor. What did u of x equal? E to the indefinite integral of whatever this was, right? Whatever this thing was. And what is that? It's box, and that box represented this. We'll go back and fill it out in a minute. But importantly too, what's the dummy here? E to the indefinite integral of whatever that is, d what? D what, everyone? D, yes, dx. Oh my, that's awfully large. Or, in other words, the integrating factor is e to the indefinite integral of n sub x minus m sub y all over n dx. There it is. There we go. Now, remember, this is the integrating factor if we assume, right? If we let it be assumed that u is a function of xy, which means, that u, a function of xy, is just a function of x. So here's my question for you that I want you to duke out for a minute. Well, actually, maybe I'll duke it out after I show you the result on the right-hand side. I think you can see, without us having to go through every single step here, that in the other case, where we make the assumption that u of xy is a function of y, the result here is going to be very, very similar, right? And maybe as an exercise, you'll want to fill in the corresponding proof on the right-hand side just to talk yourself through it. But in the event that we make the assumption that u is just a function of y, then the other integrating factor that's a possibility, mu sub y, will be e raised to the improper integral of n sub x minus m sub y all over m. Dummy, please. What's the dummy? Dummy. Yes, dy. Okay, so here are the new integrating factors that turn a non-exact diffie-q into an exact diffie-q. My question to you is the following, and then of course I will give you the answer. But before we do an example, okay, here's the question for you. When you have a differential equation, in fact, let me just put one up here so you can have the kind of an object to debate. Okay, so let me just put this one up here. Let's do this one. You ready? I'll just pull number 33 from your text. I'll write it right here. You're going to solve 6xy dx plus 4y plus 9x squared dy equals 0. Here's my question for you. In the course of solving this diffie-q, how do you know which integrating factor to pick? To give you a little more of a hint, is there any relationship between how complicated m is, right? Because, m is right here, the original m, I should say, and how complicated n is there any relationship between how complicated m and n are and the integrating factor you should choose to make the diffie-q exact? Because that's really the task now here, right? Because when we're turning a non-exact diffie-q into an exact diffie-q, the big question is going to be, how do we know essentially which assumption to make here? And the question of how do you know which assumption to make here really begs the question, how do we know which integrating factor to use? Is it advantageous to pick one over the other? And the answer is yes. What I want you to think about is using this question alone, which is a pretty, non-threatening one here, this diffie-q, see if you can come to some kind of consensus over, what clues would point you towards choosing which integrating factor. and then replay me. All right. Okay, so watch what I did here. I just compared the two integrands up here. I compared these two integrands, and when I compare the two integrands, you'll notice the numerator is the same. No, dinner time is soon. Where's Dad?
He won't do it.
Okay, when he gets back, he'll get dinner. And there's a slice of pizza in here. Go ahead, grab. There's just the last Supreme pizzas in there. I ate one. The numerator is the same, but look at the denominators, right? If you look at the denominators, you will see that the result is either here or here. Whoops, I boxed too much. Either there or there. So the takeaway here is if m, it depends on the denominator, right? If m is simpler, choose the integrating factor where the assumption is made is that mu is just a function of y. If n is simpler, choose the integrating factor where mu is assumed to be just a function of x, okay? Also, as I just kind of went about this, I noticed I dropped a negative somewhere in my derivation. Like literally I dropped a -1 because these numerators on the integrating factors, they should be, one is n sub x minus m sub y. This one should be m sub y minus n sub x. Okay, somewhere around here, I dropped a negative somewhere. We're not gonna belabor that. Let's just go change this, okay? But the big picture, you get the big picture. This numerator here should be m sub y minus n sub x. My apologies. Then really, so should this be. But our conclusion is the same, everybody, right? Because m sub y minus n sub x, it is true that the numerators are the same in terms of their algebraic difficulty, because, right? You understand? Okay, so this should be really doink, 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 doink. Okay, sorry about that. 6 minus 18 should be, it's like -12. Yeah, I dropped a negative in my derivation somewhere. Oh, that silly negatives. Well, if anyone finds where I dropped the negative, you know what, I'll give you a lollipop. All right, everybody, so now let's go ahead and solve this Diffie-Q. Let's do it. Let's take it all the way through. We're going to solve this Diffie-Q choosing an integrating factor, which is going to be, so we're going with this choice, right? So mu is going to be e raised to the indefinite integral of 2 over y. Dummy, please? Dummy, please? Yes, dy, which equals e raised to the power of 2 ln y, which is just going to equal what, everyone? Yes, y squared. Y squared is what we're going to multiply this Diffie-Q by to turn it into an exact Diffie-Q. So my new Diffie-Q becomes 6xy cubed plus 4y cubed plus 9x squared y squared. Oh my goodness, Miss Yam, what happened to my dummies? Dummies, whoops, dx plus dy equals 0. We now have a differential equation in total differential form. We just turned it into an exact, but let's just, for kicks, just check that the partial derivative of our new m with respect to with respect to y, is in fact equal to the partial derivative of my new n with respect to x. Okay, m sub y here is going to be 18xy squared. N sub x is going to equal, here it is, boink, boink, 18xy squared. And now we have an exact Diffie-Q. Woo-hoo-hoo! Yay! 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 All right, everyone. That was a great lesson. That was so fun. I will post the homework on this, and I'll actually, you know what? I'll just do it right now. I'll call this classwork/homework. You can just begin this right now. Okay. I'll put it up here right now in a second. Here's classwork/homework. Really fun. 40 is going to be a nice discussion question that you guys can have amongst yourselves. And I will see you really soon, everyone. Great job. Goodbye.